Okay, so good morning, one and all, and welcome you all to a brand new session of webinar for the JMAG FEA tool. So today we will be looking on a particular topic called the automatic searching for a current phase that obtains maximum torque and evaluating the torque characteristics. My name is Sadeep, and I am working with the JMAG team for PWSIM Engineering Solutions, Bangalore, India. The technical section will be covered by our application engineer, Mr. Joseph. So I'll just give you a brief intro of our company, and then I will hand over it to Joseph for conducting the technical session. So PowerSys is our parent company, and we operate by the name of PWSIM in India. So we have around 17 years of experience in the field of software, technical sales, and consulting. And we have around 8 offices spread across the globe with around 40 to 50 employees as of now. So these are our complete list of product portfolios. We started off with PSIM in the year 2002, followed by the acquisition of JMAG, SIME, and Smart Control. And if you see further during the timeline of 17 years, we have acquired some few other like EMTP, Sabre, Pro LB, PowerForge, Flownex, etc. So we have a complete portfolio for the simulation of multi-physics environment. And PWSIM was created in the year 2018. It was a consortium between PowerSys France and ProSim India. So we operate as the Indian subsidiary called PWSIM. So we have around 8 offices across the globe. We have offices in Germany, France, in the US, and in South Asia. And today we invite you all for this new interesting topic, which involves the torque optimization and a new function called analysis control, which is happening within the JMAG software. And I hope you will be all enjoying the session. And if you have any queries, you can directly post it on into the chat session. We'll be there able to help you. And you can send your inquiries to the JMAG support solutions email ID. So now I will request Mr. Joseph, our application engineer, to proceed with the technical perspectives of the session. Joseph, if you can start.
Good afternoon, one and all. This is Joseph, working as JMAG support engineer in PWSIM Engineering Solutions in India. So, without wasting our time, we will go through the contents of the session. We will roughly go through the contents. It will start with the problem definition. We'll go through an overview of the analysis, and we can see the assumptions which is taken in the analysis, and we'll roughly talk about the analysis model. And we will consider some design variables, and according to some geometry, we will be doing the analysis. And you can see the evaluation flow, analysis flow, and the studies which is performed over this application. And we will be going through the results, and we will compare the results with the 2 or 3 models. And finally, we have some observations based upon the results. So coming to the problem definition, as you all, so this is especially for this IPM type of motor, which is basically used for electrical vehicle applications. So you can see in a low speed torque region, you can see the torque is irrespective of the speed, and this torque is defined by the phase angle, and also the design variables which is already there with the motor model. So coming to the analysis, you can see in such situations, current phase should be fixed in order to optimize the torque, or we can achieve the maximum torque, and that will differ based upon our current phase. So a particular current phase should be selected in order to maximize your torque per the specific geometry that you have already selected. So this is how you can see the problem definition analysis. And uh, sorry, just a second. So coming to the overview, you can see we will be going through three rotor geometries. Their a current phase study will be selected or will be performed over these three rotor geometries in order to get the optimum value of this phase angle in order to get the maximum torque. So we can see the motor average currents and torque ripple are evaluated using the obtained current phases. So in the assumptions, you can see we are going to analyze a 48 slot 8 pole IPM machine. You can see a full model geometry here. So in the analysis, we'll be comparing three geometries. So it won't differ in the stated dimensions. Here for the sample we have taken, we are changing some of the parameters like magnetic width and the position of the magnet from the center, and also the slit angle available in the flux barrier area. So these are the general assumptions which we have taken. So here the inner radius of the stator or motor thickness are approximately the same. So we are not considering much of the casing part. So coming to the analysis model, as you know, we are considering the 2D model here in order to reduce our simulation time. And the partial model is done because here, as you know, here the number of poles are 8 and number of slots are 48. So when we are taking the LCM of or least common multiple of these two factors, we will get the periodicity as 45-degree angle. So the magnetic flux and all other condor, which
Jo-
periodically
sorry,
change.
Joseph. Sadeep here. Yeah, your voice is breaking in between. Can you come closer and little closer? Yeah.
Yeah, yeah.
Okay. Okay.
Hope I am
Yeah.
audible now.
Yeah. Now it's clear. Now it's
Yeah,
clear. Yeah.
yeah. So as we already explained, the periodicity of this magnetic field will circularly occur along with this. So here you can see for the next 45-degree also, the magnetic fields are the same for the existing model. And also you can see the motion region is set to the rotor part. So these are the analysis part which we are considering. So coming to the design variables and evaluation geometry, as I have already explained, you can see three geometries here. The first one is geometry 1. There you can see the position of magnet is coming closer to the outer periphery of the rotor, and you can see some of the slit angle differences in compared to other two. So coming to the geometry 3 and geometry 4, you can see the magnetic width and slit angle is changed, and performance analysis is done for all the three rotors. So here in the diagram, you can see I have specified it in a red spot, like what are all the parameters which we have taken: the magnetic distance from the center, slit angles SA, and magnetic width MW. So these are the parameters which we have taken in the analysis. So coming to the studies performed, you can see here in the first stage, we will be going through the inductance calculation and current phase search study. And in the second analysis, we will be getting the optimum current phase from the first analysis, and we will be performing the analysis in order to get the torque average and torque values. Coming to the third analysis, we will be comparing the results with the calculation which we have previously performed, and the analysis which is done with the FEA simulation. So all these are, even though all these analyses are done in JMAC Designer, we will be having some scripting in the first application. So we won't be getting deep into the FEA in the first analysis. But in order to plot the torque and torque ripple curves, we will be doing the torque analysis study 1. So in the later stage, we will compare torque analysis study 1 and torque analysis study 2. So coming to the evaluation flow here, you can see case 1, case 2, case 3 are depending upon the geometrical differences in the stator and the rotor and rotor magnets. So here, what we are doing is the inductance values are calculated from 0 to 60 degree with 10-degree increments. So there are total 7 cases that will be performed over the analysis. So we will get LD, LQ, ID, IQ value, and also the phi value from the inductance calculations in the first analysis. So here you can see in the right side, we will be getting the inductance calculation. From there, we will be receiving the values and using the scripts. So here you can see a box for searching the best current phase that provides maximum torque with the torque formula. So here the values which we are getting from the inductance calculation is assigned in the torque formula, and it is calculating the best torque, and it will show at which phase angle it is generating this much torque. So this is the overall idea of evaluation in the first stage. So here you can see after getting the results, we will plot the average torque and torque ripple values. So coming to the analysis flow, for ease of understanding, so as I have already explained, we have the first two studies. So these are executed in a sequential fashion, which means it is grouped into an analysis group study. So the inductance calculation and current phase search study, along with torque analysis study 1, is grouped, and it is performed in a sequential way. So this is the analysis group here. So we have prepared a model according to the geometric changes, and we will run the analysis group. So in the first stage, we will be performing the inductance calculation, and we will be doing the post calculation scripts in order to get the current phase search. So it will execute for this much cases. Say for an example, if you have 7 incremental divisions. So here I already explained that we are changing the beta value from 0 to 60 degree with 10-degree increments, which means 7 cases will be there. So for each case, we will check for the best current phase, and we will be storing the phase for future analysis or for generating the torque and torque analysis. So here you can see torque is obtained from the torque formula. A search is performed for the current phase that provides maximum torque, and current phase beta is set for the further analysis. So here the further analysis means we will be generating the torque for 1/6 of electrical angle period, which means we are just considering only a single period for the torque waveform, and we will obtain average torque and torque ripple from the values which we have received from the current phase search. So this is what the sequential operation means. So here you can see uh, in the inductance calculation. So as you already know, we have our study. The first study is for beta searching, which means the phase angle will be searched in order to get the maximum torque. So we have certain models, like we need to go through the sequence, like we will be going through coil and circuit modeling as shown in the diagram, and we'll be going through the motion modeling. We'll be performing the motor inductance calculation. So in JMAC, we have the default condition for calculating the motor inductance calculation, motor inductance values. So it is shown in the line here, and the motion, we can specify a fixed speed there, and using the search bit option. So here you can see in the post calculation script, you can see the best current phase is searched over a particular values for inductance, and we'll be discretizing our time and spatial factors. Say for an example, we'll be discretizing our mesh model. So it is very important in order to get a perfect torque waveform or perfect analysis. you need to go through the proper settings in the mesh. So spatial discretion means we will be performing the mesh settings. We'll be doing some mesh settings in order to get the proper value. So this is how we can do the analysis. So here you can see the motor inductance tool is there. So this is in the right side, you can see the project manager window. So this is the overall idea of motor inductance calculation tool. So there you can see the calculation range. So there we can specify whether we are going for amplitude phase analysis or we are defining axis or q-axis current. So according to that, you can fill the entire sheet. So here in the connection, our motor is connected in star connection. So here the current frequency is, as you already know, is fixed like Pn by 120 and number of motor poles. So here n poles is the total number of poles, which means 8. So here the current amplitude is like I amp. So it is already fixed like 315 amps, and a phase is set from beta minimum to beta maximum. So here this is how we are doing the analysis over the entire range of uh, beta. So here the values are assigned like this, and the number of divisions is div beta. So these are the parameters which we have set in the motor inductance calculation tool, which I have already explained here. So coming to the current phase values, current phase results, we are automatically running a post calculation scripts in order to obtain the torque value for each current phase, and we will be setting the current phase where the torque obtained is maximum. So this value beta is saved or it is set on the reference table for further analysis. So as you know, this is the torque equation which I have already explained, and there you can see the phi value where phi f is the maximum armature flux value here. So coming to the post calculation script. So uh, as I have already explained, in the post calculation script, you can see a visual VB script here. So this is the thing which I am going to explain just now. So here you can see in the post calculation script, uh, the data are defined, or you can see the phase ID value, IQ, LQ, LD, flux and torque values are defined according to its data size. So it is called for and yeah, defined like that, like a dim flux. In the bracket, you can see the type of data. So in set app equal to designer, the function calls GMX current study. So in the next analysis, we will be getting the data input from the GMX current study. So case number we are getting from the analysis from the existing case which is executed there in the analysis, and division beta is also obtained from that analysis. So overall we can see case number, division beta, number of poles are retrieved from the JMax application study. And coming to the number of poles here, that also called like app dot get analysis group dot get design table dot get equation. So this endpoint which is colored in green color, which is colored as a green, is retrieved from the analysis. And here in the set table data, you can see we are retrieving a table data from the inductance analysis which we have already performed just now. So here you can see there will be some index. So I will be changed from 1, 2, 3, 4, 5 up to 7, and you can see a table will be tabular data will be arranged. So we will be retrieving the data from the existing inductance calculation. So here you can see phase I, ID, IQ, LD, LQ, flux, and torque values are find out from the inductance calculation, which is performed in JMAC Designer. So this post calculation script, this VB script is just calling the app, our designer application, and it is retrieving the data from inductance calculation tool in order to calculate the torque value. So in the loop, here you can see the loop is executed from I is equal to 1 to division plus 1. That is, which means the calculation is performed from 1 to 7. So we have total of 7 cases here, and the torque value is compared with the existing torque value. So here you can see in the Tmax, we are initializing the Tmax and beta optimized value into 0 stage, and we are analyzing or we are performing the loop here. So in the loop, it will compare whether the existing torque value is greater than the current torque value, and if it is greater than the existing torque value, that value is saved in the Tmax. And according to that, the particular value which correspond to the Tmax will be saved in the beta optimized variable also. So this comparison will be done over the entire calculation range of 7 cases. And in the end, you can see this script returns the optimum phase angle for the respective case number to the study. So here you can see, so it is setting a user response variable as beta, and it also returns the case number for which case number it performed that study. So this is how we can done the analysis by retrieving the data from motor inductance calculation, and also we are setting the values for beta which correspond to the best torque value which we have obtained. So coming to the time discretion. So time discretion means the properties which we have, which we are mentioning in the study properties. So as you know, motor inductance calculations are performed with magnetic field analysis in JMAG. But here our aim is only to get the inductance calculation values and other flux and current values, IDIQ, LDLQ values. So here it is, our aim is not to get the magnetic field analysis or complete magnetic field analysis here. So even though it's a FE analysis, we are not performing it for many steps. The calculation is performed in a single step for this particular analysis. And coming to the spatial discretion, you can see we need to set the element size based upon the gap between magnet and stator. So fine element should be set in the overall area of which covers the outer circumference of the rotor core, or we can say it is set on the outer periphery or air gap in a smooth way. So torque waveforms show variation with time referring to the rotor position. So it is necessary to prevent gap mesh from being distorted. So we need to get a accurate mesh here, and we need to get the accurate data also. So if displacement per step is an integral multiple of the element size, it will reduce this calculation error, or it will avoid the element distortion in that particular area. So we'll set our divisions for one electrical angle period equal to slot per pole by 2 into division per slot. In order to calculate, in order to capture the slot harmonics, one slot displacement of rotor in circumferential division, we can see it covers 4 times integral multiple. So we are considering the circumferential divisions like this. Circumferential divisions is equal to the divisions per electrical cycle, one electrical cycle, and it is multiplied with integer value in order to avoid the error, calculation error. And it is you can see here only half electrical angle is taken here in order to cover this circumferential division analysis. So and apart from that, we will be setting a rotational periodic boundary here, and we can see the symmetry for mesh also when we are setting the rotational periodic boundary here. So as I have already explained, we have gone through the inductance calculation and current phase search study. So we already received the beta value and also the case value, case number from the existing analysis. So uh, you can see here, we started with inductance calculation and current phase search study, and we are coming to the next analysis, like the torque analysis. So the results which we have received from the inductance calculation and current phase search study is retrieved or is fetched into the torque analysis study 1. So here you can see the beta and case number is noted, and it is given to the torque analysis study 1. So here you can see this is the torque analysis study 1. So here we will in the properties of this current source, we will set this value for optimized beta. So here you can see in the red indicated portion, you can see the beta value here. So to evaluate torque characteristics and in order to obtain the average and torque ripple value from the existing calculation, we are doing this FE analysis. So as you can see here, no other details are changed compared to the previous case. Here you can see motion modeling is same as the above. Circuit modeling is done here, and time discretization and spatial discretization are the coming modeling data. So here we'll start with the motion circuit modeling. Here you can see the beta value which we have retrieved from the post calculation script or from the initial analysis is given here in terms of a variable known as beta. So coming to the project manager window, you can see our aim is to generate a response data with respect to the each case. So we will be generating the torque average and torque ripple, and we will be plotting the graph according to these particular values. So this is how we can see the values. So coming to the time discretization. So here, as you know, initially we have done the analysis for only for one step because our aim was to get the motor inductance value. But here our aim is to plot the torque value and we need to get the torque ripple rate from the existing analysis. So for that we need to have the time discretization. So only one torque waveform period is selected in the analysis in order to reduce the calculation time. So here you can see according to the parameters we have mentioned, the time step increment dt is given as 1 by f by division per electric sector. And coming to the number of steps, you can see we have calculated it over a 1 by 6th of electrical angle period, which means one torque period is equivalent to 1 by 6th of the electrical angle period. So it is divided by 6. Division per electrical angle is divided by 6, and it is added with 1 in order to which correspond to the next step, or it should not start with 0. So coming to the studies which we have performed, so here we have gone through two things. The one which in which we have calculated the inductance and other values, and we have returned the beta value and case value to the existing study in the torque analysis here. And now our aim is to get the data for torque analysis study 2. So here what we are doing is we will simply generate a torque curve and ripple rate plot with existing beta case beta which is optimized, and we will compare these existing results of torque analysis study 1 with torque analysis study 2. So in the torque analysis study 2, which we are going to do now, comprises of the phase angle which varies from 0 to 60 degrees. So this torque analysis study 2 is just to compare the results which we have received from the post calculation script. So in order to check the accuracy of the model, we are doing this torque analysis study 2. So here, instead of getting a proper value from the beta, we are just performing the beta A. So here you can see in the right side portion, in the circuit model, you can see beta A new variable is defined. Actually, it's not a new variable, it's the same variable only. So here this beta variable is here this beta variable is varied over the range from 0 to 60 degree. So this is how we can change the difference. So here the parametric analysis is only based upon optimized rotor geometry, and we are doing the parametric analysis over the beta, which ranges from 0 to 60 degree with seven uh, 7 cases. So this is how we can see the results. So next we will go to the comparison plot or analysis results here. So before going to that, we will go through the analysis here. So this is the JAMAC designer window here. So here you can see we have created an analysis group as I have already explained. So here in the initial side, you might have gone through the analysis group. So this is the analysis flow, and we have created a group for that. So in the first analysis, you can see uh, two studies have performed within this group. So as you know, analysis group can be created by right clicking on the project model, and you can see create analysis group. So the main advantage of this analysis group is we can have a sequence for the operation which we are going to perform. So here, if I am editing this analysis group 1, you can see in the order, you can see I have performed the operation for searching the beta, and I have performed the motor NT calculation, basically based on the FEA calculation. So these two studies have performed in a sequential order. In the first phase, it is getting it is retrieving the beta value, and in the second thing you are getting the torque value. So this is how we can perform the analysis. So here you can see the studies which is coming under the analysis group. The first one is search beta. Second one is the motor NT curve analysis. So here you can see I have already run the model in order to save the time. So here you can see I have plotted, I have registered the beta value which is optimized from the post calculation scripts. And in the second stage, I have created torque average and torque ripple value for the existing beta case. So here I have plotted that. So you can see here. So here you can see in the table we have performed analysis for 3 rotor geometries. So the beta value which we have received from, or which we have returned from the post calculation scripts uh, are as follows. For the first case, it found 30 as a best optimized value, and in the second stage, second rotor geometry, it is found that 40 is the best or optimum value for the beta. And in the third, you can see 40 again. 40 is selected as the best beta value for the current analysis. So according to that, you can see the torque values also here. So for the first rotor geometry, so hope you remember this geometrical specifications here. So we have done geometry 3, geometry 1, 2, and 3 here. So according to the variables which we have mentioned as a parameters, like MP, MW, and SA, we have performed the analysis using the post calculation script here, and we have found that 30 is the best value for case 1, and 40 is the best value for case 2, and 40 is the best value for case 3. So but again we can see here the maximum torque is obtained for the rotor type of case 1. So maximum torque is obtained for this particular rotor geometry 1, and there we can see the value which we have received as average values 58. So this is how we can see the results. So coming to the graph, you can see, or you can plot the same thing which I have explained just now in this way. So you can see the 30. So these are the angles which we have performed the analysis, and 30 is optimized value. And here you can see case 2 and case 3 are we are getting the maximum value for case 2 and case 3 as 45, and here you can see 47. So from this particular analysis, so we have found that our geometry 1 is getting the maximum torque with minimum phase angle, that is 30-degree phase angle. So this is how we can see the results in response data. So coming to the analysis group, so the thing which we have performed here, so this is the first 2 analysis which we have done here. So these 2 studies we have grouped in under analysis group 1. The same thing is grouped there. And coming to the third analysis, so here you can see, which I have explained in the slide, you can see here. So under the condition, you can see the motor inductance calculation tool. So this is motor inductance calculation tool. So the thing which I have explained there are already explained here. Project manager window. So calculation tool. So in the motion region, you can see speed is defined like this as a variable here. And coming to the boundaries, so you can see the mesh settings here. So here, as I have already explained, the mesh is defined for each part. So here you can see minimum animal size is given for the air gap area in order to reduce the error which occurs during the rotor rotation. And here you can see element size is defined for each particular part. So we can generate. And as I have already explained, we have performed the analysis for only for 1 steps, because our aim is not to get the magnetic field analysis data. Our aim is to just to get this motor inductance calculation data by using this motor inductance calculation condition here. So this is performed over 1 step, the first case. And in the second step, you can see, as I have already explained, we have performed it for 17 steps with time step equal to this. So I have already explained about the number of steps calculation and time step calculation here. So I have performed like that. So, and we are getting the results. So we already have seen the values here. So the same thing is explained here also. In the analysis group, we have obtained the torque value here that we have received from the motor entity calculation. So now what we are going to do is, so we already found that the beta value and torque value here. So here already we found that case one, in which case one we are getting the maximum torque. So for the same case one, existing rotor geometry, we are performing the motor entity calculation with FE analysis. So here you can see we are performing this FE analysis only for case one of rotor geometry, and there you can see the case control. So when I am showing the cases here, so you can see here. So here you can see our parameter is beta A, and that means which we are parameterizing the beta value here from 0 to 60 value with 10-degree increments here. So we are just finding out the value. We are just finding out the best beta value available for getting the maximum torque. So instead of this post calculation script in the third study, we are just parameterizing this this beta value, and we are just calculating and comparing the results here. So coming to this, you can see in the results for this also I have done the analysis. So here, as you can see, I have plotted torque versus beta. So here you can see from I have performed from 0 to 60 6 increments. So in the 10 you can see we are getting around 52.52 Newton meter, and in 20-degree beta angle you are getting 56, and at a particular angle of 30-degree we are getting the maximum value 58.2496. So we are just performing the analysis only for case one compared to the analysis which we have done previously. So there, in order to save the time for comparing all these results, we have used post calculation scripts in order to get the optimum value for beta and optimum value where we are getting uh, the rotor torque value. So this is how we can see the results here. So we are just comparing this. Actually, here you can see here also the torque value is obtained for 30-degree phase angle. There also we have received the value for 30-degree angle. This is how we can see the ripples also. So here when I am clicking on ripples, here you can see the maximum ripple is occurring at a 40-degree angle. So we need to operate at a particular angle of 30-degree in order to reduce the ripple. So here you can see the ripple rate is like 24 percentage, 24.37% here. So if you are performing the, if you are rotating your motor with 30-degree beta angle, we will be getting the ripple rate as 24%. So this is how we can see the analysis. And compared to the results here, so comparing to the results here, so initially we have done the analysis for case one, case two, and case three. So there, as I have already explained, we have performed the analysis with increment from 0 to 60-degree. But this analysis is done in post calculation script instead of doing it in FPA in order to save the time. So we will be getting the data for case one. That means for 30-degree, we got the results for 58.58, and we got maximum torque for at 40-degree for case two and case four. So this is how we can plot using an Excel sheet, and comparing the results for torque ripple and average rate value. Here you can see in the case one, means existing rotor geometry, we got at we got a 58.58 value for at 30-degree, and for case two and case three we are getting much reduced value compared to the first value. So but coming to the ripple rate or ripple ratio, here you can see it is more for this case two geometry. There you can see it is formed at a particular angle of 40-degree. So this is how we can see the results. We can plot the ripple ratio and average torque value with respect to the results which we have obtained from Geomax Designer. So coming to the observational part. So in the observation part, we can see we are comparing the results. So there are two analyses. So even though the two analyses are based on FEA, we can say the second one is more into FEA. Because in the first one, we have found that we have used the post calculation script in order to reduce the time required for the calculation. So we can say like the second analysis is purely based on FEA, and we are comparing the results which we have received from the torque equation and we are getting from the FE analysis. So here you can see uh, the value is almost close to the analysis. In the torque formula, you are getting more torque compared to the FE analysis because there we are not considering the variable value for inductance. Or we can say the saturation is not considered in the first case, which we have performed using a torque formula. But again, if you want to if you want to see the results based upon the saturation factors, you need to do the analysis based upon the FA calculation. So this difference is because of this fixed value calculation based upon the post calculation. So we can see, but again we can found one more thing. The best angle or the phase angle is 30 for each case. So here you can see, even if you are doing the torque formula also, the phase angle is found at uh, found found at 30 degree in order to maximize the torque. And again, if you are changing it into FA domain also, we are getting the maximum torque value in the 30 degree value. So here you can see the geometry finalized based upon our calculation. So this is how we can see the results. So this is all about our observations and the analysis. So hope you have gone through the analysis and the procedure in which we are following this thing. So as I have already explained, we have covered through the inductance calculation. We have gone through the three rotor geometries with specific variables like magnetic width, slit angle, and magnetic distance from the center. In the second stage, we have performed the inductance calculation study, and we have performed the post-calculation script analysis in order to get the maximum value like this using this post-calculation script. And in the second analysis, that means the torque analysis study, by using the existing beta, which we have found from this we have returned from the post calculation script. We have done the analysis, torque analysis study one, and here you can see the beta which is assigned here in the torque analysis study in order to get the maximum torque value. And in the third analysis, we are just comparing the results which we have performed using the post calculation script and which we have found from the FE analysis. And we are just comparing these results, whether it's right or wrong, or whether it is appropriate or not, in order to have this FE calculation. So we can say it's an advantage over the FEA. FEA analysis is having much advantage over the torque analysis, but when compared to large design data or large design templates which we are having, in order to save the time, we can reduce the time by using the scripts, and we can finalize a beta value, and we can finalize the rotor template for which we have optimized our torque value. So we can see all the results, and later you can analyze the torque analysis study too in order to have a better understanding of your particular model. So this is just for the saving our analysis time, and in order to find out the maximum torque value and maximum current phase angle that corresponds to the torque value. So this is all about the analysis and observation. So it's all about this current phase tracking. So thank you all. Thank you for participating in this webinar, and hope this information will be useful for you in further analysis. So you can send your queries, and if any salient query is there, you can directly send a mail to jmangsupport@powersys-solutions.com. So for detailed information about our company, you can go to www.powersys-solutions.com. Please feel free to contact us. Thank you. So if you have any queries, you can either you can send it to gemaxsupport@powersys-solutions.com, or you can contact your nearby office. Mr. Haridas, hope we can wind up the session.
Yes, Joseph. Yes, I think we can wind up the session. Yeah.
Thank you.